Now, hello everyone. We are excited to have you here and want to welcome you to Flatiron School's Intro to Data Science, Simulations Using Python. My name is Corey Mickelson, and I am the event coordinator here with Flatiron School. A big part of my job is hosting these free introductory workshops like tonight's event to give you the opportunity to meet some of our instructors and get a better feel of the Flatiron School experience. A quick reminder, we are going to be using the chat as our main source of communication, so make sure you set that little blue button from host and panelists to everyone so we can all chat together. So without further ado, I'd like to introduce our host for the evening, Daniel. He is one of our lead data science instructors. Go ahead and take it away, Daniel.
Awesome. Thank you, Corey. Like I said, my name is Daniel Birdno. I'm one of the data science instructors here for Flatiron Data Sciences program. I've also been a Flatiron alumni and a Flatiron data science coach. So I've gone through kind of the whole process, working myself up. So very familiar from the student standpoint, as well as kind of all aspects of the teaching. I actually see a few of, or at least one of my students in the audience. So shout out to Marshall. Thank you. Today, we're going to take a look at running simulations in Python. What does that mean? What does that look like? Why we might do that? And then we're actually going to set it up for a very specific game. We're going to take a look at Risk today, the game Risk, if you guys are familiar with it. In chat, throw it in chat if you've played Risk at all. If you're familiar with the rules, we're going to talk about a bit of them. But the idea here, right, why do we run simulations? Well, we can think of these as something called Monte Carlo experiments or Monte Carlo methods. The idea here is we're relying on repeated random sampling in order to give us numerical results that we can then analyze and speak to. We're going to use some aspect of randomness here to solve a problem that we can determine by running this a whole bunch. Think a dice roll. We're going to see that quite a lot. Risk has a lot of dice rolls in it. Think card games. This is very, very popular in board games and card games and betting games. The idea is to simulate running this a bunch of times without actually running the game, so we can determine our best course of action as a player. Should we do one thing or should we do another one? Which one is going to give us the best chance of success or the best chance of winning the game? Because that's always the goal, right? Unless we're playing whose line is it anyways. These are primarily used in three different classes of problems. Something called optimization, which we're not going to dive too deep into today. How do we optimize an algorithm? This is something we cover a lot in our data science program. How do we tweak an algorithm to get the best result? Also used in numerical integration. And then the third one that we're interested in today is generating draws from something called a probability distribution. Probability distribution, measuring the likelihood of something happening, the chance of an occurrence, right? If I roll a dice, what's the chance of getting a 1, a 2, a 3, a 4? Well, those chances play into a game that involves dice rolling. We can model those chances and simulate a dice roll or a bunch of dice rolls against each other and create, for lack of a better word, a simulation of our game. Brief graphic here, right? Everyone knows pi, 3.14. But we could solve for pi a whole bunch of times and get a pretty good approximation, right? On our squiggly equal sign instead of our actual equal sign. We have an approximation of what pi is to some level of a digit, right? We've got 4 significant figures here. Now, let's shift to thinking about a game and how we're going to simulate that game. We need to create an event space. We need to define our game in some kind of rules. How does our game work? How does it determine a winner? How does it set conditions, or other words, rules or limitations? How does it confine the player from only rolling 2 dice, etc.? So every game is going to have some kind of event space. These give us an idea of how we play the game. This is very common. Show of hands in chat if you've ever heard of reinforcement learning. Yeah, very basic level. Think Pavlov's dogs. A reward system, right? Reinforcement. If you do something correct, I'm going to reward you. That means you're probably going to want to do that thing again. If you do something wrong, I don't reward you, or maybe even punish you, although, you know, that can be debated. But you're going to not want to do that thing again. That's the very simple concept of reinforcement learning. For a game, right, for our event space, we have these conditions, these rules. If you do this thing, right, if you have a higher dice roll, you lose an army. If you hit 0 armies, you lose. Right? Pretty basic. We can equate that sort of relationship or that structure of our game to create our simulation. We can take what is a dice roll, a very simple task, and we can repeat it in nauseam, indefinitely, over and over, or however many times we want to, 1,000 times, 100 times, 200,000 times. We can simulate that dice roll. From that simulation, we can get our data, or simulated data. We can analyze that data and take a look at making some concrete decisions about how we play the game. So let's take a look at building a simulation for the game Risk. And we'll go through, we are simplifying the game Risk here. If you are familiar, I know some of you popped in there that you hadn't played, or you know it, but you hadn't played, or you have played. We are going to simplify our game a little bit here to answer a pretty specific question. Right? We've got Risk, it's a board game. You're essentially trying to take over the world. The object is to conquer all territories on the board by eliminating your opponents. Well, how do you eliminate your opponent? You fight them, you attack them. How does Risk determine who wins in a confrontation? Well, we have essentially some rules that Risk is defined by. We have 2 armies of size N and M, right, respectively. Size Army 1 N, Army 2 M. These are battling each other. We have an attacker, right, the person whose turn it is, and we have a defender, the person whose territory that they're trying to take over. We have A and D. According to the rules of Risk, the attacker can roll up to 3 dice, depending on how many armies they have, right? They can roll up to 3 dice. If they have more than 3 armies, they can only roll 3 dice. If they have less than 3 armies, they can only roll as many dice as they have armies. On the other side of it, our defender can roll up to 2 dice. Again, he has to have that number of armies. We then compare the highest dice rolls from our attacker and their defender and the second highest if our defender has rolled 2 dice. Any ties go to our defender, but we're going to take the highest dice roll as the winner. What that looks like in principle or in practice, we have a couple different examples here. We have an attacker rolling 3 dice and our defender only choosing to roll 1. The attacker's dice is higher, our defender loses that troop. Another example that could happen, right? Our attacker rolls 3 dice again. And this time our defender decides to roll 2 dice. Our first highest pair, the attacker wins. So our defender is going to lose 1 troop. But our second highest pair is a tie. And so we're going to do the tiebreaker to the defender. So our defender loses 1 troop and our attacker loses 1 troop. We could have where they both roll 2 dice. Right, our attacker rolls 2. Our first highest pair goes to our defender. So the attacker loses 1 troop. Our next highest is a tie. Again, the winner goes to our defender. So our attacker now will lose 2 troops. Another example we could have, right? If we only roll 1 dice, our defender could try and roll 2 dice to beat that 1 dice. In this case, he didn't, and he loses 1 troop. Now, the concept here is that you as a player can decide how many dice you want to roll based on some kind of trade-off. If I'm a defender and I roll 2 dice, and I only have 2 armies, and I lose both of those rolls, I've lost that territory. The attacker fully wins. On the flip side, right, if I'm an attacker, I could roll all 3, but I could also lose some of my armies because the defender wins a tie. So the defender has the tiebreaker advantage. So what we're going to try to determine today is which one of these advantages is better? And does it depend on your army size? How many troops do you actually have to essentially gamble with? So we're going to try and decide or determine if the attacker advantage, being able to roll an extra die, gives them more of an advantage in winning a fight than the defender's advantage of breaking all ties in their favor. Well, the way we can do that is we can simulate a whole bunch of different battles, right? Different armies against each other to get a potential, right, a hypothetical synthetic result from our simulation. We will definitely share the notebook after this meeting. Yeah, it'll be part of the recording. It's a good question. We could simulate all these games, all these battles. We can tally up all of our results, who wins, who loses, by how much, etc. And then we can plot that. We can visualize our results to analyze them, right? We can now maybe determine which one of these advantages is better. Now, let's start really simple. We know we have dice rolls going on. We know we need to incorporate dice rolls. We need to simulate rolling of dice a whole lot of times. And we can do that with Python very easily. I have 3 different packages we're going to use today, or different libraries. There's a couple different names for them. These are going to help us within Python to run all of these simulations and set them up. I'm not going to go super in depth into, yep, in chat. I'm going to simulate a dice roll. I can call to my NumPy package, right? This gives us randomness and mathematical calculations. We're going to have pandas help us represent our data and visualize it. And then matplotlib is going to help us plot it in a graph. These are very standard packages, Peter, and very standard aliases. These are probably the 3 most common. The 4th one would be something called scikit-learn. That's what we use here at Flatiron for all of our, not all of it, but most of our machine learning. Very, very popular. But yeah, these are very common. I'm not going to install them. I already have them installed. If you guys are grabbing this notebook after the recording, when it's being sent out and want it to run, you're probably going to want to uncomment these to install these packages so you have them on your end. Once I've installed them, again, I'm not going to run them because I have them installed. I can import my packages. We're going to set a style for our figures. We're going to make them look cool. We want them to have all the same style. Standardization is good. And we're going to set a random seed. This is for reproducibility. There is absolutely a way to look at source code. Yep. Pandas, just Google like pandas documentation, and you'll find their full documentation and source code. Okay. Stephen, I'm using our Flatiron environment that we have curated for our curriculum called Learn Environment. Students get pointed directions to help set this up the first week of program. It allows us to handle all of our curriculum in the same platform, which is really nice. But now let's go back to rolling a dice. I can use NumPy to simulate a dice roll between 1 and 6, right? Every time I do this, it's giving me a random value. A dice roll, or at least a evenly weighted dice, right, has an equal chance of 1, 2, 3, 4, 5, or 6. So we can take this little bit of code and we can run it 10 times in what we call a for loop. For every number in my range of 10, we're going to go ahead and run our random number. Now, we can go one step further and define this as a function. And so we don't have to keep copy and pasting this. We can call our function over and over and over again. I'm defining my function. I'm going to call it roll die. That's the blue text there. All my function is doing, is running our random dice roll, 1 through 6. I have that function defined. I can now use it. I'm going to save it off my result as my roll. Just doing one roll here. And I can print it out. I rolled a 5. I rolled another 5. Oh, I'm really good. I rolled a 4. Right? We can keep rolling a dice over and over again. This brings us to next step, right? We can simulate a lot of these rolls. We're going to roll 6,000 times. We're going to do lots of dice rolls, right? If I were to sit at a table playing Yahtzee or something with a little cup, I love Yahtzee. It's my favorite family game growing up. We could roll 6,000 dice. That would take me a really long time. I can set up some code. I'm going to create an empty dictionary. Yeah, this is called F-string format. We're not going to dive too deep into it. It's a way to format strings, aka our quotes. A string is a very specific object in Python. And so we can formulate our string. In this case, I'm going to tell it to always print out I rolled a with my simulated die on the best. But we want it to put in our roll every time we do a roll. So this allows us to have this print statement be very dynamic. If my roll changes, I have a new roll, it's going to insert itself into my string, my statement. The underscore there is just to, right, if we did a comma, notice my green text changed. Python syntax can have some very specific nuances, subtleties. So I could do it as 6,000. But we could also do it as 6_000, just for ease of reference. So if I had like 6, is that million? Yeah. Better readability, right? What is that number? We're not sure because we're pretty used to looking at right commas. Well, if I separate all my tenses, I have 600 billion, I think. Someone correct me if that's not right. Numbers are hard. So it allows us for just readability because we can't use our comma like we could with sort of standard text, standard English. Now, I'm going to do all these rolls a whole bunch of times, and I'm essentially going to count up all of my different values. Every time I get a different dice roll, right? Every time I roll a dice, every 6,000 times, I want to know what my result was from that roll. We're going to save that off to our dictionary called num frequency. I'm going to create a key value pair. This is something we have with dictionaries. Not going to go in depth into that today, but what we're doing here is rolling 6,000 times. We are counting up or saving off every time we roll and the result that we get. And we're adding it to our dictionary so that once we're done with our 6,000 rolls, we could take a look at all of our rolls. We had, 950 ones. We had just over 1,000 twos. We had somewhat close to 1,100 threes, et cetera, et cetera. Now, throw it out in chat, right? This is an even dice. There should be an equal chance of rolling every number. In theory, right, on paper, if I rolled 6,000 times, every option should have 1,000 rolls. But that's not true in reality because each roll is independent of each other. And so the more rolls we make, I'm going to come up here and change this. We're going to go one more 0. The more rolls we make, the closer we get to our hypothetical probability, right? We're evening it out. The less rolls I make, the more variance I have in my counts. So the more simulations we can run, the more robust our simulation is, the more times we go through this process. Exactly. Yeah. This is related to a concept of uniform distribution, but also a couple other things. So I'm going to turn this back to our 6,000. Right? We can simulate a whole bunch of dice rolls. Notice it changed. Right? I did 6,000 new rolls. This took me 2 seconds to run. It took a little bit longer to set up, but is going to be untoldly amounts faster than me sitting there and rolling 6,000 dice and, checking off a graph paper or something. Obviously, this is the power of Python, the power of our computers. Well, okay. We know that we can simulate a dice roll. Well, now we need to formulate what that looks like in the context of risk. We have multiple dice for both our attacker and our defender. And we also need a function that's going to compare these to each other. Right? What did my attacker roll and what did my defender roll? And what is our result? Who won? So, excuse me, we're going to set up some helper functions. Again, we're defining a function called roll_attacker. And it's going to take in an argument. We're going to give it the number of armies that the attacker has. This is going to return us a list of sorted dice rolls that that attacker made. Number of attacking armies. Now, let's recall back to the rules of risk. Our attacker can roll up to 3 dice if he has 3 armies. If he has 5 armies, he can still only roll 3 dice. So 3 is our max, regardless of how many armies. But if he only has 2 armies, he can't roll 3 dice. So we need to equate for that. Right? This is one of our conditions, limitations of our game that we need to factor into our simulation. If there are no armies, right? If not n armies, if we have no armies for our attacker, we're not going to roll at all. This is just protecting ourselves against zeros, basically, against nuns. Our number of dice is going to be our minimum, whichever one's smaller, either 3, because that's the maximum number of dice you can roll, or the number of armies that our attacker has. if he has 2 armies, we're going to result to the minimum 2. If he has 4 armies, it's going to result to 3 dice. We then create those rolls by using our roll die function for every number in the number of dice we have. So if I have 3 dice, we're going to roll 3 times. If I have 2 dice, I'm going to roll 2 times. We're also going to sort those in reverse order. So we get our higher values at top. Do the attacker defender know up front how many die the opponent will roll? Yeah, Scott's got it there. The attacker first is I'm trying to think of the right word. You tell them you're going to attack, and then the defender, you tell them how many you're attacking with, and then the defender gets to choose. That's kind of the defender advantage, one of them. Why the range call? Yeah. Good question, Don. We're looking at here is, right, we have this number of dice that the attacker needs to roll based on either the minimum or their number of armies. In order to accomplish that, we can call our function roll die, right? That's going to roll our dice once. We can call that every time we loop through our number of dice. The range is to give us that list, right? We have 3 dice. Range 3 is going to do 1, 2, 3. So we're going to roll die first die, we're going to roll second die, and then we're going to roll a third die. And we're going to put all of that into a list. This is something called list comprehension that we cover decently in depth in the first phase. Curious Marshall's thoughts on list comprehension. It could be very powerful. It could be, agreed, yeah, written out like a for loop. Yeah. Y'all will click easily. I'm really bad at typing. I want to print out my numbers. Now 0, because Python is 0 indexed. So our 0 is our first roll, our 1 is our second roll, and our 2 is our third roll. With the if not. Yeah, so what it's saying, basically, if not is a way to check if n armies is 0 or doesn't exist, right? We didn't give it a number. Yeah, he can't really. We're saying if not, we're saying if this doesn't exist or it's 0, do this. So if we don't have armies, we're just going to return no rolls. That's kind of our check condition. Well, if we do have armies, we're going to go ahead and go with our rolls. And yeah, Scott, there are some nuances that we're kind of hand waving over when we actually look at the risk rulebook in order to accomplish this, but sometimes you have to do that. You have to make assumptions. We haven't talked about like different territories and different cards, but I'm going to run this. We now have a function that can calculate our rolls for our attacker based on the number of armies that they have. Our attacker has 5 armies. Here's a sample attack, a simulation. We have 3 dice rolls. He did pretty good here, 6, 6, 5. Not as good, right? We could keep simulating an attack. Well, we can do the same thing for our defender, right? We're going to define a function called roll_defender. That's also going to take in, right, the number of armies our defender has. Same code here, except we're changing our 3 to a 2 because the defender can only roll 2 dice at maximum. The rest is the same. We have sample defender rolls, right? I can keep simulating this as many times as I want. Okay, well, we now have 2 rolls or two list of dice rolls, let's jump back to the rules of risk, right? What do we do when we roll the dice? Well, we're looking at the first highest pair. Who's ever higher wins. The loser is going to lose an army. If we then have two dice, we look at the second highest dice roll. And again, the higher of the dice wins, the loser loses an army. So we need to compare these two lists. Our compare rolls function is going to help us do this. What we're giving our compare rolls is the result of our roll defender and our roll attacker functions. Right? This list of rolls returns rolls. Also, we're returning them sorted. So we know that the first roll is going to be the highest roll in our list, always. This allows us to, sorry for the scrolling, we can return the number of armies to remove from each side, right? We can equate to what happens after our dice rolls. What do we do? What rule do we follow, right? What path? So first thing we're going to do is set up a variable, both for our attacker, our attacker and our defender. We're going to set them as 0 to start, right? We're going to set a counter at 0 because no one's lost yet. Now, we're going to combine our two lists, our attacker role and our defender role. Zip is a really handy function within Python that's doing this for us. It's going to zip these two together so that we can compare them. We're going to save that off combined as something called zipped underscore rolls. We then need to compare them, right, to determine who wins and who loses. Our zipped rolls contains both the attack roll and the defense roll. The zip turn them from a list of ints to a list of tuples. I think so. Yeah, I'll have to check if it's a tuple, actually. But that is a good question, Nick. It depends because we have two lists here. Should be, yeah, it should be like that. Well, we can now go into that and say that if our attack roll is greater than our defense roll, our Pac-Man, we're going to add our defender loss up by 1. If can I print zipped poll? You mean zipped rolls? Yeah, here we'll do. I do need to give it actual. We're going to give it our sample attacker and our sample defense. I now have zipped rolls. And we have a zip object. Because, yeah, we can check what kind it is. It's a zip. Now, what I can do is show you how we're unpacking that. I can print attack. Let's do it. Yeah. Let's print attack. Oh, you're not gonna like that, are you? Print attack, print defense. Let's go there. There we go. So we can see a bit under the hood what's going on. I'll leave that there. Go ahead and save it. But essentially what we're doing is making that comparison. If our attack die roll is greater than our defense die roll, we're going to equate that to our defender losing. Otherwise, we're going to equate it to our attacker winning. Else, Python looked like a lot like JavaScript. Yeah, we're not getting into that. But yes, somewhat. All we're doing then is returning our number of losses for our attacker and the number of losses for our defender. Go ahead and define that function. Right, recall we had our sample attack and our sample defense. We can feed that into our compare roles function we just defined. Right, we're passing it our sample attack and our sample defense. And we're going to give our loss for our attacker and our loss for our defender. Here are the roles we had. Looks like our defender lost twice. He's going to lose 2 armies. That's just one example, though. Okay, well, let's equate this to our actual game of Risk again. Right? We now have something that can give us a winner or loser, essentially, for a particular attack. Let's say that each army has 5 armies. Right? Our attacker has 5 armies, and our defender has 5 armies. We're then going to set a round counter, because we can keep doing this round after round, right? Attack after attack. If you don't take it over the first time, try again. Well, that's good to hear, Philippa. Show of hands in chat if you've worked with RStudio code, because that's what I started with. I have a marine biology background, and Python is innumerably better, in my opinion, my professional opinion, than RStudio. I know it's changed quite a lot, but something about R just gets me on edge. Maybe because I took classes about it in college. Python over R every time. Yeah, absolutely. You can write Python in R, so might as well. Okay. What we're doing here is using a while statement. Have not, Peter. We can run this loop as long as we don't have 0 armies. Right? As long as our attacker and our defender have at least 1 army each, we can still attack and defend. Right? The second one of them gets to 0, they lose that territory, or they lose the attack. So we are just going to print each round, right? What's happening. We're then going to set our attack, right? Here is our roll dice for each. Here's our attacker rolls, and here's our defender rolls. Notice we're using our functions we defined earlier. That's why we defined them. If you roll a 4, a 6, and a 3, it would put them as the second roll as the first roll. The order of the rolls doesn't matter for Risk. You're just going to roll 3 dice simultaneously, and the defender is going to roll his 2 dice simultaneously, or 3 and 1, 2 and 2, etc. That's a good question, though. Yeah, sometimes order does matter depending on the game. Right, I think like Yahtzee. If you've ever played, I can't remember the name of it. It's a dice rolling game, but it'll come to me. Okay, so we have our rolls, our attack and defense roll. We're comparing our rolls. We have our attack and our loss, right? Coming out of our compare rolls function. Now I can take my armies and I can minus every time that they lose, right? Every time they lose one of those dice comparisons, they lose an army. So every time, right, we have a loss, 1 or 2, we're going to subtract that from their respective armies. So every round we go through, whoever loses is going to lose an army. The next round, they're only going to have 4, maybe, or maybe they lose 2 and they only have 3. We're then going to print out what they've lost, so we know what's going on each round. And then we're going to advance our round just by increasing that number. So we know that we're at our second round, and our third round, and our fourth. Then finally, we can print out how many armies they have remaining. Here's our first roll, or our first round, right? We start with 5 armies each. We have an attacker roll and a defender roll. This time, the defender lost both. We go to our roll number 2. Our attacker still has 5 armies, but our defender only has 3. They've already lost those 2 from the first roll. Well, this time, the attacker loses 1 and the defender loses 1, right? Comparing our 5 to 5, defender wins the tie, or our 3 to 2, the attacker wins. Well, now we're at 4 and 2 armies. We can roll again. This time, our attacker lost both. So now we're at 2 and 2. We're going to roll again, and this time, again, our attacker loses 2. Final results, the attacker has 0 armies or lives remaining, and our defender has 2. Our defender wins. I could keep running this and get slightly different values, right? It's simulating all these different rolls. Okay. Well, all we need to do now is put that into, hey, Robert, put that into a function. So that we can use it over and over and over and over again in repetition. Right? We can simulate all these different events happening. So that's what we're doing here. We have a new function we're calling run_simulation. I'm going to keep saving because make sure. We need to give it our attacking armies, our defending armies, and we're going to say verbose equals false. If we want to display what's happening each roll, we could say verbose equals true when we call our function. And I'll show that, demonstrate that on what's happening there. But what we're doing here, right, is just going through the same thing with our while loop, right? While we still have armies for both our attacker and defender, we're going to simulate each round. Well, I now have a function that's going to do this for me. Let's try it out, 5 and 5. What is this returning to me? Well, let's take a look at our function and what we're returning. We're returning our attacking army minus our defending armies. A clean sweep. Yeah, Nick, that's actually pretty rare for us that happened to us, but that's the nature of randomness. What happened here is we have 5 attacking armies and no defending armies. The attacker won. We can get an idea, right, from our printout if I set my verbose equals true. Now our defender won, right? 0 minus 3 gives us -3. Let's test it again. Now we have the flip side. Ooh, we're getting lucky here. Our attacker has 0 remaining, and our defender has 5. -5. Okay. Well, now that we have our run simulation function, let's run it 1,000 times. Rather than me just click it 1,000 times and run it, we can save our results off as a variable, and we can do another list comprehension. We're going to run our simulation with 2 armies for each, for every number in range 1 to 1,000. There's our 1,000 simulations. All right, we're going to do this. We're going to run our simulation this many times. We can look at the first 10 results. And looks like we got defender winning, and then our attacker, and then our attacker, then our defender again. attacker, defender, 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 defender. We have some results. Well, I could count those results. Right, these are just our first 10. Oh, sorry. We're indexing here into our list. I could look at the first 5. Really the first 6. No, first 5. Getting crazy. I could look at first 100. Now, that's going to be hard for us to really look at, but we could go back to the first 10. We now have a count of our different scores, right? The different options from a game with 2 armies each. We could plot those using matplotlib. Not going to cover too much on the syntax here, but we're setting a figure space for our figure, for our visualization. We're going to create a horizontal bar chart using our index here as our using our index as our y and our count as our x axis. We're going to give it some labels because we want nice and pretty visualizations that everyone can understand and read. But here's our results for our 2 armies versus 2 armies that we ran 1,000 times. The attacker wins 2-0 or 1-0, or right, no one, there would never be a case where nobody wins because we have a tiebreaker, right? Defender always breaks the tie. We also have the times the defender won by 1-0 and the times they won by 2-0. And we have our count, right? How often that occurs. Now, right now it's looking like, okay, maybe the defender, right? Especially in this bar here, winning quite a lot more. We have only run 1,000 though, 1,000 simulations. So we're going to explore this a little deeper. And we also only looked at results of 2 by 2. We could find our mean, right, across all of our instances. And we could interpret this mean. That could be 516, but that's okay. When an army of size 2, right, 2 and 2, fights another army of size 2, the defender is expected to win by a margin of 0.516. This is changed because of the randomness. Right, on average, our defenders are winning by a little bit. Yeah, for the dot mean, we're calling our NumPy package. We're just getting our average. So a mean is what we call a measure of central tendency. We have mean, median, and mode. So the 3 most common. Our mean is going to give us the average. So all of our results added up, divided by the number of results we had. Okay. Well, we want to look at this problem across a whole range of army sizes, right? We just looked at 2 army against 2 army. We want to look at 3 army against 3 army, 3 army against 4 army, 5 army against 5, so forth. Well, I guess, I don't know if 5 is the maximum. I haven't played Risk in a while. But what we can do to compare all of those is normalize our results. Why? So we can compare simulation to another simulation. Our victory counts above is a raw count, right? All it was if we look at our, sorry for the scrolling, our function, just, right, our attacking armies we have left minus the defending armies we have left. We can actually normalize that mean that we're getting from here to be proportional to the starting army sizes, right? We're going to divide our mean by the size of the army or armies. So we are essentially, right, if we have a 2 by 2, we can compare it to our 5 by 5. How are we going to do that? Well, we're going to define another function called normalized mean. Give it our army size and the number of simulations. What are we going to do here? You'll hopefully see a pattern. We keep nesting the functions we keep defining inside each other. We're going to create results that's going to, run our simulation for army size for the number of simulations we've told it. We're then going to get our mean results, our mean, our np.mean, our average. And then we're going to take that average and divide it by our army size. This is our normalization. This is a very common practice in data science. We can normalize data, we can scale data, standardize data, very common, especially for things that are distance related. Think comparing two different heights or height and weight. We want to make sure they're on the same scale. Okay, well, let's quickly compare the same simulation from above. We're now bounded by -1 and 1 instead of our -2 and 2. This is what our normalization did. Go ahead and plot that again for us. We're now going to do a non-horizontal bar chart, switch it up a little bit. Again, our -1 and negatives are our defender winning, and our positive is our attacker winning. Okay, well, we're getting really close. Let's go ahead and set a variable called n simulations to be 1,000. So we can go ahead and pass that variable in multiple times instead of having to type out 1,000. And I probably forgot to run this cell. If the function's not defined, it's not going to work. I've got to run the cell to define the function. That's on me. Let's go ahead and check out for armies of 1, 1 versus 1. Let's try 2 versus 2. Let's try 3 versus 3. Let's try 4 versus 4. Oh, we've gone positive. We'll notice that we have a switch at some point from the defender winning to the attacker winning on average. Well, let's plot these results so far. What am I taking a look at here? I'm setting some colors based on some list comprehension. With some blue. Mean versus average versus median. Mean and mean and average are the same. Two different words for the same measure of central tendency. Median will be the middle point for your data. So from either side, counting up your values until you hit the middle. Mode will be the most common value in your data set. We're going to create another bar chart here based on our winning margin. Yeah, okay. So here's our relative margin of victory. Here's your army size. As we're increasing army size, seems like our defender advantage is getting worse. We're switching, Our defender advantage is good with low armies, and our attacker advantage is good with large armies. Well, let's do this in Notion because we have a simulation to do it. We're going ahead and define another function that's going to plot our results for our simulation based on army sizes. Here's our plotting function. Notice we're calling our normalized mean function. I can give it a list of army sizes, and it's going to loop through all those different army sizes and perform these calculations, just like we did up here. Let's show that again, right? Same or similar graphic, right? It's a little different because it's a simulation, and it's actually simulating dice rolls, right? All 1,000 of our dice rolls are not going to be the same every time. I can keep running this. We're going to switch a little bit. But we do see this pattern where our defender advantage, losing my voice, shows up quite a lot at low army sizes. Well, let's do this for a lot of army sizes. Let's do this for army sizes from 1 through 20. Let's keep our 1,000 simulations still. We're going to tweak that in just a second. Let's go ahead and do what we are having our function doing, right? And plotting. We can use our plot results for n simulations. It's going to take a bit more time because it's got to run through all 20. Okay. We have a pretty clear picture on what's going on here. Right, we see that our defender advantage, again, right, shows up at low army sizes. The larger our armies get, right, on average, our attacker advantage starts showing up, comes into play. So we can now use this information to hopefully beat our family at Risk. I'm very competitive with my family, and I always lose. Would it was near parity with expect? We're gonna bump up our iterations, but maybe not to 1,000,000 because we'd be here for a while. But, right, notice we gave our plot results for n simulations. And right, Ian, the more times we do this, the more robust our results would be. The more I'm going to trust my results because it's based on a larger simulation, right? Recall that dice roll, the simple dice roll. The more dice rolls we have, the more our distribution of 1, 2, 3, 4, 5, 6 is going to look even. The lower simulations or the lower dice rolls we have, the less even that's going to be looking. So, right, we have an n simulations argument for our function. Well, we can change that, right? It's going to run n simulations every time. We'll see where, let me find it for you guys. Right here, right? We're passing that into our normalized mean function. Well, let's come here. I'm going to give myself a new cell. I'm going to just copy and paste. Wait, no. One cell below. Let's still do, I'm going to limit it to like 10 for sake of our time. And then I can say n simulations equal, let's try 10,000. And just to demonstrate, I don't need the underscore. For this, and what did I call it? I've got a match. It's underscore. Okay. Or it's rather lowercase. And I'm going to let that run. Let's see. We've got a question. Do attacker and defender have the same number? For our simplified version of Risk, yes. Someone would have to correct me who has played Risk lately. If they don't always start with the same number of armies, that I'm not sure about. Okay. We ran even more simulations. Now, the more simulations I run, the longer and longer this is going to take, which is why I reduced our army sizes a bit. But the more simulations I run, I'm running at 100,000 right now. Again, the more robust I am in my results, the more confident I am in my results, because they're based on more iterations. We've run this ad nauseam over and over and over and over again, compiled all results. And we've run it 100,000 times. That's a pretty comfortable level of simulations. We could run it 1,000,000 times. We could run it 100 million times if we had the time and computational power. No. So the underscore is just taking the place of what would be. I'm going to let this finish. What would be a comma? We can't do the comma because Python will get mad at us. I can give a new cell here just to demonstrate, right? My 1,000 is green integer. My 1,000 or 1,0,00, right, is not all green. So it's not one full integer. Scott. Yeah, I think, didn't we include, let's see. We might not be able to pass it in, but we included it in here. We included it in our run simulation, verbose equals false, which is in, I'm gonna have to come back here a bit, right here. Verbose equals true. Can't run that yet until it stops. So let's go back down here. Oh, it finished. Perfect. Just in time. So let's try this out. I'm not positive this is going to work, but it's a good investigation. It's half the fun. I was in my verbose equals false. So run simulation. We then nest that into our normalized mean. So set verbose equals true. We then nest that into our plot results, normalized mean. Okay, let's try it. Let's just try it on our first one. Aha, we can. No. Oh, like a progress bar. No, sorry. Okay, yeah, I see what you're saying, Scott. Unfortunately, we don't. That is a very interesting question. There are some algorithms where we can set a verbosity. These are, given to us in packages that are going to give us an idea of how far along they are. But we don't have anything like a progress bar for our code cell running. It's going to depend on, just see if you want to wait to finish or, oh yeah. Something I wish we had. It would be really awesome. It is also going to depend on the power of your machine. If you're running a supercomputer that's connected to Google or something, or AWS, it's not as simple as that, but you'd have a lot of access to a lot more computing power than I would. You could even possibly do something called running this in parallel, where I'm going to run 100,000 simulations, but I'm going to run half of those on my computer and half of them on your computer. So hopefully it takes less time. Or maybe I'm going to run, a subsection on all 135 of us on 135 computers. Cool. Okay. Kind of like torrents. Peer-to-peer network. Absolutely like torrents. We won't talk about the legality there. But yeah, you can set up a network, like a peer-to-peer network. Okay, let's see. We've got some questions. This printed out quite a lot of results, but we got the end. We've built a pretty substantial simulation, right? We walked through a whole bunch of functions, all the way from simulating a simple single dice roll to simulating a set of dice rolls, to comparing those dice rolls to each other and determining a result or a winner, to simulating a full battle, right, from start to finish. When an army reaches 0, they lose, right, until one side is eliminated. we also are tracking those results. We've also touched on why we normalized those results. So we could compare our margin of victories across our different sizes. And then finally, right, we've visualized our results, giving us a pretty good idea on some strategies we can use while playing Risk. It wouldn't be possible that every time you finish, absolutely possible, Christine. I could print out that counter. That's a good suggestion. Find out the minimum number of attackers needed to beat 5 defenders with less money. Yeah. We could try and optimize our play. Now that's a bit more of an in-depth problem or an in-depth question, but what Thomas is getting at is, can we essentially try to optimize, right? Should I always roll 2 or 1 dice as a defender, or maybe as an attacker, right? We didn't really touch on the concept of choice here, because you don't have to roll all the dice. We've kind of treated that as our assumption for this game, which is why this isn't quite Risk. We're doing a sort of a more simplified version of Risk for the battles. I think someone had that earlier. I'm scrolling up through chat here. Question for the future: how would you model the whole game? Okay, yeah, it was Ian. Highlight, simulate the choice variables of the game, like a choice of where to move on the board. Game stages where there are forked trees, simulation of game results, and battle interactions. Yeah, you would have to. It can be really hard to model that concept of choice, right? That would be us trying to optimize. As the attacker, do I always roll 3 dice if I have 3 armies or more? Or, well, maybe if my defender, right, if we're dealing with small army sizes, I don't. Or if I have a lot of big army size, I'm going to roll a lot of dice, because our simulation has showed us that on average, I have a winning margin in that category. That would lead my choice as an attacker. Now, the stuff that we can't super well simulate about Risk, at least I haven't seen it, I haven't digged too much into Risk simulation, but would be the concept of, I think, right, Risk has different cards that represent like different army amounts. There's a lot more that goes into the game, like how you set it up and that kind of thing. Who goes first? We could obviously simulate that, but awesome. It sounds like you guys are quite enjoying this. Does the advanced class simulate Axis and Allies? Not quite. Only the what's the old school RTS, Red Alert? Anyone remember playing that game? I'm a video game nerd. Let's see. I'm trying to get to all of them. Do we have Don? What was Don's question? Okay. You had the, I'm finding it here. Let's see. Yeah, you could, to a limited varying degree of success. This is the idea behind like predictive machine learning modeling, where we're going to train an algorithm, a model, on a whole bunch of previous data that we have that has ground truth. So like I have a whole bunch of car data about features of my car, right? How long it's been around, the maintenance on it, how often it's got an oil change, the miles on it, even the color if you really wanted to, although that probably doesn't matter. Not a relevant feature. You could feed all that information, right? We know that we have a label, right? This car broke down or something about it stopped working. We could try and predict that based on all of our previous car observations. And our model is going to try and learn on what causes a car to have that problem. if we have enough data, we have good enough data, and we have the right features that are equating to a car breaking down, we can predict that, you know, a car might break down based on our suite of features. Any source for your favorite simulation book? 3 Blue, 1 Brown. I think Marshall can attest. It is an amazing YouTube channel. I believe it's a single individual. I could be wrong. I'm trying to remember his name, but very amazing, very high produced. They cover a lot of stats topics. He covers a lot of data science topics, everything from distributions. I'll get you here. 3 Blue, I believe that's it. 3 Blue, 1 Brown. Really cool. Definitely worth a check out. It's a YouTube channel. There's a lot of other good ones. I'm trying to remember sort of some of my favorites. Median, if you're looking for blogs, has a good, I don't know what they call it, an aggregate called Towards Data Science. That is all just articles about data science techniques and thoughts and projects and like I said, techniques and methods and things that are changing. So definitely take a look at, I'll put it in chat as well, Towards Data Science. And it'll be from the platform Medium, which is a pretty good blogging platform, in my opinion. Blogs are, sneak peek, if you're interested in the data science program, is one of the requirements for our program. The idea being that it helps you network, helps get your name out there. A couple of graduates have actually found jobs from their blogs. It gets you writing both technically and sort of retrospectively. So it could be a really good practice if you're just jumping into a topic. As you're researching that topic, you're going to be reading blog posts, but maybe think about writing your own blog post about, hey, I'm diving into simulations, and maybe try and simulate one of your favorite games, right? Whether it's a card game, we can simulate the drawing of cards, right? We have a deck of cards, just like we could have die. Now we have a lot more cards than dice, but same kind of concept. That could be pretty beneficial, right? If you're starting to put it down on paper as you're learning it, can help you really solidify what you're learning. Highly recommend. Please don't read my posts. That's all right, you can. Clock. Bright side of mathematics. Cool. Thank you for the suggestions. Do I know any good places? The Flatiron campus building is an amazing place in New York to code. It is in, I think it's still in the Flatiron building, right? Maybe not anymore. I think you're muted, Corey. I think they've moved.
It's in the financial district at 11 Broadway.
Cool. Yeah, an excellent place to
come on and stop by on Thursday. We have campus tours every Thursday from 1 to 2 p.m. So please, if you would like to come and check out the campus, you are more than welcome.
The promotions write themselves?
The link to the Jupyter Notebook will come after, along with the recording of tonight's presentation.
Trying to think of some other good, there are lots of good YouTube channels for this kind of thing. I'm trying to think of one. Can't remember the name of it.
Oh, I bet that's fun. The simulation of Monopoly.
Ooh, yeah. Has anyone, show of hands, has anyone heard of the Monty Hall game show? Where you've got 3 doors and there's a car behind one of the doors? What do you think? Should you switch doors or stay with your door? What is everyone thinking? Always switch. Always switch. Yep. We talk about this in the data science program, where we talk about something called Bayesian reasoning for probability, but the result, or the result of a simulation of the Monty Hall problem is that you should always switch. You have a 2/3 chance of winning the car if you switch versus a 1/3 chance if you don't. So always switch. If you're in that situation. I don't think they still run a game show, but.
Also, if anybody's interested, I dropped the YouTube channel in there. That's where all of our event recordings go after we send them out to everybody that attended. So if you want to check out any of the other data science videos that we've put out, that will be there. And then I dropped the link in the chat earlier for the next data science event. That's actually in 2 weeks, since we end things a little bit early in December. And that's going to be on decision trees.
Oh, those are my favorite. I will not be giving that, but I love them. And by association, random forests, which are just a bunch of decision trees. They're amazing. Really cool. Would
Believe
absolutely.
Mark Barber is going to be hosting
Yeah,
that.
yeah. He's one of the Flex instructors. He's awesome. He's been here quite a while. He's an OG.
Yeah, what was it? He did a Tech in 20 event for me last week about
Ooh.
data literacy.
Oh, I kind of want to watch that.
I can send you the link.
Yeah, please do. Actually,
His background's really fascinating.
Yeah, I haven't talked to him too much because he's on the Flex team, but he's a good guy.
That's what Slack is for. Just bug people all the time. I'm also dropping our TikTok in there. We've been having a lot of fun with this lately. So if anybody wants to check it out, I always try to send people over there. If you have any questions, we do host monthly admissions, like info sessions. The next one is going to be on I believe the 14th of December. And then we have some new events rolling out for next year. We're going to be moving some stuff more to the daytime so that our friends across the pond can also join us. So we'll be doing webinars from 1 to 2 p.m. as a lunch and learn, as well as some learning on demand options for people that have tougher schedules to work with. So I hope that everybody gets excited for that. And I just want to thank everybody for coming out tonight. We really appreciate you. And I apologize for the last minute time change. We wanted to make sure that everybody could come, and our host is the most important person. So we got everything accommodated, and still a large group of you showed up tonight. So thank you. Did anybody have any last minute questions? Thank you. The notebook will be sent with the recording. So you'll receive an email from Flatiron that like thanks you for coming, and then there'll be a link to the video and then any of the materials that we used.
Thank you all for joining. Really awesome. Glad to have the chance to talk to you guys.
Thank you, Daniel. Okay, y'all, have an amazing evening, and we look forward to seeing you again soon. Have a good night.